even without Euler's formula, a great benefit can be drawn from the observation that we made yesterday, which is if we define this function of real variable alpha to be this combination, then this function of real variable with complex values, so complex valued function of real numbers, has, I guess, one fundamental property, but it's overwhelmingly fantastic. And that is, I'll write it in this order, that if you apply it to a sum of two numbers, it's equivalent to finding the product of the values of the function. So in many ways, it acts like an exponential. In fact, this property pretty much defines an exponential function within a multiplicative constant. Not a multiplicative constant, but almost defines. Is it a multiplicative constant? I don't think it's a multiplicative constant. But within an appropriately placed concept, pretty much defines the exponential function. And Euler's formula certainly takes advantage of that, plus more. But even without Euler's formula, a tremendous benefit can be drawn from this formula and its exponential-looking property. And many of the applications lie in trigonometry. So this, in a way, connects trigonometric functions with exponential functions. Even though we haven't yet written this in exponential form, that's going to happen in about 10 minutes. The connection is already there, and it can be exploited, and it can be exploited in a way that's not earth-shattering, but in a way that creates a tremendous amount of convenience. It is known that trigonometric functions are kind of cumbersome. The identities are long, they're hard to remember, but exponential properties are nice and clean. You never have to look up a property of the exponential function because it's just pretty much obvious every time. And so this relationship alone, without Euler's formula even, pretty much gives you all of the benefits of applying the simplicity of exponential functions to remove the complexity of trigonometric functions. I'll give you one example. I'll give you two examples. I'll give you 1.5 examples. I'll give you one complete example and one almost completely worked out example. So, a special case of this formula is if we take alpha and beta to be the same number, and then we find out that f of 2 alpha, and we can even generalize it to n, which means that, now let's take this formula and plug in what f represents. Cosine n alpha plus I sine n alpha equals this combination, where we can use the binomial formula. So this identity gives us instant formulas for cosine of any integer multiple of an angle. For example, and we're going to do most of the work in our head, what is cosine of 2 alpha? Well, we have to plug in 2 for n here, and then because cosine represents the real part of this expression, we simply have to collect all of the real parts of this expression. And I think at this point we're pretty good at multiplying complex numbers, so when we square it, we'll have cosine squared alpha minus sine squared alpha. Now, this is not a mysterious identity at all. In fact, it follows from one of the basic trigonometric identities, which, however, you need to remember. For sine 2 alpha, we just need to pick out the imaginary part, and which will be 2 sine alpha cosine alpha. Now let's go to third power, which will give us cosine of 3 alpha. Now that's a formula that I surely don't remember. But I remember the structure of the binomial formula, so whenever I need this, I just have this picture in my head with a third power here. and I mentally collect the real parts. So the first one comes from this being cubed, and this term being raised to the 0th power. And then the other term corresponds to when this has a power of 1, and this has a power of 2. That's correct. And because we're squaring this term, and it has I in it, it'll pick up a minus sign. And there's the binomial coefficient of 3, so it becomes... So I don't remember this formula, but I remember this connection and produce it on demand whenever I need to. And the binomial formula is so structured that you can pretty much do it with any power, as long as you remember the binomial coefficients. So sine of 3 alpha, picking out the imaginary terms. The first one will come from the term where this has a power of 1 and this has a power of 2. And there will be only one I in the mix, so it'll come with a plus sign. So I will actually put it here. It will be, once again, a binomial coefficient, the binomial coefficient of 3, then one of these, and 2 of these. And the other one will come from this being raised to the 3rd power and this being raised to the 0th power. Now here we'll have I cubed. Taking out I squared gives us the minus sign, so we end up with minus sine cube of alpha. And so we're obtaining trigonometric identities and basically working with trig, but in a way that mimics working with exponentials, or at least polynomial powers. So that's a fantastic application of this observation.